So in this video, we're going to look at household chemicals. In particular, I'm going to focus on soaps. So to start out with, we need to make sure we remember the difference between polar and nonpolar compounds. If it's a polar compound, that means that it's either an ionic compound, so an ionic was a metal with nonmetals, or you have two different elements bonded together, or it's one where the dipoles don't cancel. So in this case, I can see I have a metal with nonmetals, so that would be ionic. This one's also ionic, but it's two different elements bonded together. And in this case, when I would look at CH3Cl, these dipoles wouldn't cancel. When I look at the electronegativities between C and H, carbon has a bigger electronegativity and wants the electrons more. Between C and Cl, chlorine wants them more. So these two dipoles are equal and opposite, so those would cancel, but these ones do not. So that would be an example of where the dipoles don't cancel. Nonpolar ones mean you have two of the same element bonded together, like Cl to Cl, or it could be organic compounds, where like alkanes especially. So C8H18, where you would just have this long string of carbons, and then you would have hydrogens all the way around there. That would be an example of something that is nonpolar. So when I look at soap, soap is made by reacting a fat, so it could be like oil or lard, with lye or sodium hydroxide. Sodium hydroxide is mostly used for our solid soaps. If it's a liquid soap, like a hand soap, those are usually potassium hydroxide. So we have a base, and I know it's a base because it has OH, base with fat, and that's going to make soap. This soap molecule is going to have two different ends. It's going to have a hydrophilic end, and that word hydrophilic means water attracting or water loving. That end of it is polar, and that's because water is polar, so this end that is polar likes the water because water is also polar. We also have a hydrophobic end on our soap, and this is the one that doesn't like water. It's water fearing or water repelling. That's the end that's nonpolar. So within my soap molecule, I have two ends. One that's polar, one that's nonpolar. And that's very important when we look at how a soap works. So this is an example of a soap molecule. I can see I have this big, long hydrocarbon tail. And then I have this ionic head. And it's ionic because metal with nonmetals. So this is another picture of kind of what the structure looks like. So we have this COONA at the end. Here's my COONA at the end. This would be like a molecular models when we would build models. This is kind of what it looks like. This part is the Na. So the part of this that is nonpolar is this big, long hydrocarbon tail. And the part here on the end that is ionic, that's the part that's polar. So this part of the end, this is polar, that's the head, and this whole long tail, this part is nonpolar. And that's important as far as how soap works, because the ionic part, this polar part, dissolves in water. This long part that's nonpolar doesn't dissolve in water, but it does mix with oil and grease because those things are nonpolar. So the nonpolar part, the oil and the grease, will be attached here to this long tail, and this part of it will dissolve in the water. So what happens is when you use soap, all the dirt from your body and the grease and the oil all stick around to this tail. This head part then dissolves in the water and it drags the tail on with it. This would be another example. So this is my long nonpolar tail, and here's my polar head. Now, when I have this dissolved in water, we can see these individual things. These are all my soap molecules. And you can see all the heads are facing outwards because all of the heads like the water. So the water's around here. So all the heads face toward the water. This would be a drop of oil or grease. And we can see all the nonpolar tails like that oil or grease. So they're all pointed inward here, picking up on this oil and grease. So the soap then surrounds this oil droplet, and this structure is called a missile. And that's very important to how soaps work, because if we didn't have both the non-polar part and the polar part that would dissolve in water, if it was all non-polar, it would get the oil and grease off great, but then you would just have chunks floating around in your bathtub and it wouldn't dissolve in the water. If it was all polar, it wouldn't dissolve the oil and grease. So it takes two pieces, one that attracts the grease and the oil, and then the head that's going to keep this stuff dissolved in the water. And that's how a soap works.